pleasure to introduce Kayvon Stassen, who's going to be our speaker today. Kayvon is visiting as the Dudley Hirschbach Teacher, Scientist, Lecturer at Harvard for this year. So each year we have one such visitor, which means that the visitor gets to give 2 talks, and this is his second talk. So yesterday, Kayvon's lecture was the Fisk Vanderbilt Master's to PhD Bridge Program, a model for dramatically increasing diversity at the PhD level in science and engineering. It was a really great talk about Kayvon's efforts to really increase the participation of underrepresented minority scientists in astrophysics. But today, he gets to give his astronomy talk. So Kayvon studied physics and astronomy at Berkeley, and then went on to do his PhD at Wisconsin, and your advisor was Bob Matthew, is that correct? He was then a Hubble Fellow, and then he moved to Vanderbilt, where he's now a professor. He was recently appointed as the Stevenson Endowed Professor of Physics and Astronomy, but he didn't stop there, and he became a dean.
You're not supposed to tell them that.
Congratulations. So he's now the Senior Associate Dean for Graduate Education and Research. But the exciting thing is, from all external metrics, he's been allowed to continue lots of exciting research. He's received many awards, so I won't list them all. I just picked one, which is the American Physical Society Nicholson Medal for Human Outreach. An award, I love the title of that award because I look for aliens on other planets. And he served many leadership positions in our community, including being an invited member for the White House STEM Initiative and on the board of directors for the American Physical Society. Kayvon, I do want to pause to say I really am hard-pressed to name someone else in our professional community who has done more actual, tangible work and put in real hours and time to increase the participation of underrepresented minorities in our field. Many of us are working on that problem. I'm really hard-pressed to think of someone who surpasses you in terms of the commitment to that. And I really am moved by that. And it is such a joy to introduce you because I've long admired your science as well. And we're going to hear about so much of that exciting work today. So Kayvon, please.
Wow. Thank you, Dave. Wow, such a kind introduction. And it's always just a pleasure and an honor to be here. And I'll tell you, in thinking about what I would share with you today, I decided I would do something a little bit new for me anyway. You know, I have a talk that I've given several times over the past year, and it's gotten pretty polished. I decided that there's so much exciting stuff happening right now, specifically in the lead up to TESS and with the Gaia data coming down and all kinds of exciting work. I thought I'd do something new and share with you just some of the breadth of really exciting possibilities that are being enabled with the advent of Gaia and TESS together, along with the fundamental astrophysics that emerges from the studying of eclipsing binary stars and other bodies that transit said stars. And so I had a little bit of fun with this, so I hope you'll bear with me as I sort of do a little bit of a historical intro that will be relevant to you here, as you'll see. And then after that, I'm going to launch into a bit of a shotgun approach to really just sharing with you just a broad array of what I think is really exciting astrophysics that comes out of this kind of work. But to set the stage, so, you know, it turns out that Henry Norris Russell was here in 1946. Giving what was to become the inaugural Russell Lecture. And I'll just read a little bit of the intro to you, both because, you know, none of us talk or write this way anymore, and it's just, you know, really amazing. From immemorial antiquity, people have dreamed of a royal road to success, leading directly and easily to some goal that could be reached otherwise only by long approaches and with weary toil. Times beyond number, this dream has proved to be a delusion. The easy way has ended in an impasse, and the right track has led up the hill difficulty. This has been so invariable in experience that the very suggestion that there might be a royal road is hardly to be mentioned in polite society, whether of scholars, statespeople, or saints. In the larger sense, this distrust is fully sound. We cannot expect nor hope to get anything worthwhile without working for it. Nevertheless, there are ways of approach of unknown territory which lead surprisingly far and repay their followers richly. So richly that I'm going to share with you some of the bounty of riches. As you'll see, there's probably no better example of this in the eclipses of the heavenly bodies, eclipses of satellites of planets, but our greatest source of otherwise inaccessible information is to be found in the mutual eclipses of the components of close binary stars. And he goes on to say, this has been shown they permit the determination of something which had previously been regarded as utterly inaccessible. He's referring to the fundamental radii and masses of stars and all of the understanding that follows therefrom. So, with that backdrop, historical backdrop, let me now share with you, indeed, the royal road of eclipsing binary stars and transiting bodies and all the kinds of things that we can learn. So, very quick primer for those of you who don't spend as much time as I do looking at eclipsing stars. From an analysis of the eclipses in a light curve, together with the radial velocities of the two stars, these are some of the things that we can measure. We can measure the two masses, the masses of the two stars, independently from the radial velocities and from the fact that by virtue of the eclipses, we know the sign of the inclination angle of the orbit. We also get the radii of the two stars from the durations of the eclipses. We get the ratio of the temperatures of the two stars from the eclipse depths. And so just by introducing one additional measurement, namely the temperature of the spectral type of one of the stars, now we have all of the other information. We get the luminosities via the Stefan-Boltzmann law. We get the surface gravities and the densities from the masses and the radii. We get everything. And we don't need to know the distances, which of course traditionally have been one of the really limiting factors in so much of stellar astrophysics. My research group has been working on ways to extract, to the extent possible, basic physical information from eclipsing binaries in an automated way. And so we started by thinking about sort of the standard cartoon of an eclipsing binary light curve. And as I just told you, there are certain, call them shape parameters of this light curve that map onto physical properties. The durations of the eclipses map onto the stellar diameters, the depths of the eclipses map onto the ratio of temperatures, and so on. Using ground-based surveys, such as our own KELT exoplanet transiting survey, one of the most common false positives in transiting exoplanet surveys are eclipsing binaries. And we find tons and tons and tons of them. And I will tell you that most of these eclipsing binaries are not interesting. So what we wanted to do was to develop a way of sort of separating the wheat from the chaff. And so we started this eclipsing binary factory project where we brought in various period finding algorithms, neural net classifiers, robust eclipsing binary light curve solution estimators, and we developed some ways of characterizing the properties of the light curve, of the eclipses and the light curves. We learned the hard way that you can't just do splines because then you end up overfitting the noise. And then we trained using a set of Ogle eclipsing binaries that some of you may know something about to see if we could train a pipeline like this to accurately recover the physical properties of the eclipsing binaries. And I won't go into this into detail, but this is just to convey that in fact we can do quite well with a pipeline like this at recovering the known properties of the stars just based on a neural net approach to characterizing the light curve parameters. And basically in 90% of eclipsing binaries we can recover the physical properties of the stars with an accuracy of about 10%. Now, to be very clear, that is not high enough accuracy on the stellar parameters for us to do real astrophysics, but it enables us to, as I said, separate the wheat from the chaff. And so now we have a way of identifying potentially really unusual and interesting eclipsing binaries. So we've applied this, by the way, to the Kepler data, and you can access on the MAST website some 3,000 Kepler eclipsing binaries that have been characterized in this way. But what I want to do now is to jump into a couple of specific case studies that exemplify what I mean by rare but astrophysically important and useful eclipsing binary systems. So this is one. This is a double brown dwarf eclipsing binary at an age of about 1 million years in the Orion Nebula cluster. This was at the time, and still is today, the one and only known eclipsing binary comprising 2 brown dwarfs. And so, you know, from the light curve analysis, we get the radii of the brown dwarfs. From the radial velocities, we get the masses. So these are brown dwarfs that have masses of 60 and 40 Jupiters. But notice that the radii are quite big. 2/3 of the radius of the sun, half the radius of the sun. And that's, again, because this is a very, very young system. These brown dwarfs are still early in their gravitational contraction. One of the really interesting results from the very beginning is that there's a temperature reversal whereby the more massive brown dwarf is actually cooler than the lower mass brown dwarf. And any models of young low mass stars and substellar objects predict a monotonic relationship between mass and radius, mass and temperature, mass and luminosity, etc. Interestingly, though, and this will be relevant in a little bit, the luminosities come out pretty much as would be predicted by these standard models. So there's something funny about the temperatures, but the luminosities are okay. We checked to make sure that there wasn't anything else going on in the system that might corrupt the properties, like the presence of an accretion disk or something. There's nothing like that. But so we continued to study the system for a while, and one of the things that we learned is that the 2 brown dwarfs in the system also differ dramatically in terms of their magnetic activity. So the more massive, the primary brown dwarf, is very magnetically active, at least as evidenced by its H-alpha emission. I like this picture. What you're seeing here is the H-alpha region of the spectrum of this eclipsing binary at the 2 quadrature phases. And this massive white thing here is the saturated H-alpha emission line from the Orion Nebula. It's an H2 region. But at quadrature phase, the radial velocities of the primary brown dwarf swing it blue shifted and red shifted just enough so that you can see that it is actually a strong H-alpha emitter itself. The lower mass brown dwarf, however, is H-alpha quiet. The more massive brown dwarf is spinning fast. The lower mass brown dwarf is spinning slow. So there appears to be some rotationally driven magnetic activity in the higher mass brown dwarf. Okay. So now, if I put the 2 brown dwarfs on an HR diagram, and this is a standard isochrone for a 1 million year stellar population, and I'm showing in red where the 2 brown dwarfs should be on this isochrone for their age and their known masses. We've measured the masses. And the lower mass magnetically inactive brown dwarf is basically where it should be. But again, the more massive brown dwarf, the active one, is sort of at the right luminosity, but much, much cooler than it should be. And if you were to try to infer its mass based on its temperature, you would get its mass completely wrong. So this led us to consider the effects of magnetic activity on the basic properties of low mass stars and brown dwarfs. And so we turned to a larger set of low mass eclipsing binaries involving M dwarf stars that have been studied by some of the other people sitting here in the room. And in 2012, we published a set of empirical relations linking, I showed this slide at ITC lunch today, linking the strength of chromospheric activity as measured in H-alpha with the amount by which a low mass star's radius is inflated compared to expectation, and its temperature is suppressed compared to expectation. And we then went back to the brown dwarf eclipsing binary and said, well, if we apply that empirical relation and try to infer what temperature the more massive brown dwarf would have had if not affected by this magnetic activity effect, where would it be on the HR diagram? And it turns out that it ends up back where it should have been. So this really suggested that there really was a nice relationship between the strength of chromospheric activity, presumably magnetically, presumably rotationally driven, and structural changes in these low mass stars, inflating their radii and lowering their surface temperatures, approximately in a way that preserves their bolometric luminosities. So we started then thinking about some of the downstream effects of this. So, one question that we're always thinking about in star formation and low mass stars is, what is the nature of the initial mass function? This is work that was done a few years ago in the Orion Nebula cluster, mapping out the shape of the initial mass function in that young cluster. And what's typically done in this kind of work is to measure the spectral types, measure the temperatures of the stars, and because we typically don't have direct measures of luminosity, we try to then infer the masses of the objects based on their temperatures and some isochrones or stellar models. And so that's how this initial mass function was constructed. But if some, perhaps many, of these young low mass stars are magnetically active, thereby having their temperatures lowered, thereby having their apparent masses lowered, then in fact the true initial mass function may be quite different than what we think it is. Specifically, the true peak of the initial mass function should be at higher masses, right? In other words, these higher mass magnetically active stars are masquerading as lower mass stars because their temperatures have been decreased by activity. So we actually took a look at this in another young cluster, and I'm sorry here I've plotted mass in the opposite direction. But basically, depending on the strength of the activity effect that you assume, you can see that what you thought was an initial mass function that peaked right around the substellar limit, in fact, becomes an initial mass function that peaks at a mass that's about a factor of 2 higher. So this can be a non-negligible effect on our inferences about the nature of the initial mass function at the very, very lowest mass end. Okay, so that's a lot that we learned from one eclipsing binary that led us down a road to think about the effects of magnetic activity on the structures of low mass stars and so on. There's another interesting direction that we can take this. So in the literature that has emerged around this question about radius inflation and the effects of activity on the structure of low mass stars has basically been, what is the mechanism actually for this radius inflation? So there's one school of thought that suggests that these magnetically active stars are just so heavily spotted that in essence emergent flux is being bottled up, but the luminosity has to come out because it's being generated in the core. If you bottle up some of the flux and so you lower the temperature, well then of course the radius has to be larger. Okay, so that's basically a surface effect. Another school of thought is that the magnetic fields are strong and affecting the internal structure of the star. And one result of that would be to affect the strength of convection, affect the convection zone more generally. So one way of getting at this is to look at another proxy that actually tells us something about the behavior of the convection zone in these stars. And so Garrett Summers and Mark Pincinel a couple of years ago took this idea of radius inflation and decided to ask anew a question that has perplexed many of us for decades. And that is that if you look at a coeval population in a young open cluster like the Pleiades, it has long been known that the amount of lithium, that the lithium abundances of solar type and lower mass stars in the Pleiades show this enormous range, a couple orders of magnitude at a given temperature. And specifically, this range is such that the lower envelope of the lithium abundances agrees with what you would expect from a standard model, but there's this population of stars that have that have higher lithium abundances, in other words, have less lithium depletion than what would have been predicted by a standard model of convection and mixing and lithium burning. And one of the perplexing things about this historically has been that it's been known for a long time that the highest lithium abundant stars, those stars with the least amount of lithium depletion, are the fastest spinning stars. And that was perplexing because you would think that if you spin the star faster, you might actually drive more convection in the interior, and that should move the lithium around more and cause it to be depleted more quickly. Well, what Garrett and Mark showed was that if they took a standard stellar model, shown here in red, with solar type convective mixing, but now introduced a factor that basically suppresses the efficiency of convection, you can basically explain the full range of observed lithium abundances in the Pleiades with the introduction of this one parameter, basically a magnetic convection, suppression of convection. So this is still relatively early work, but I think it really points to that magnetic fields in these rapidly rotating stars are actually having an effect on the convection zones of these stars. I'm proud to tell you that Garrett is now one of my postdocs, and just last week was awarded the Outstanding Doctoral Thesis Award in Astrophysics from the American Physical Society for that work. Okay, so everything that I just told you basically emerged from, as I showed you, the discovery of one really interesting eclipsing binary system, and then thinking about where the road richly led from there. But over the past decade, my group and others have been working hard to identify as many of these very young eclipsing binary stars as possible. And by now, we've amassed a pretty good number. There are other young systems for which we can do measurements of stellar masses and things, and those are interesting as well. I'm going to stay focused on the eclipsing binaries for now. This is just to say that we've built up a pretty good number of these. And so a couple of years ago, Willie Torres and Greg Feiden and I did a review examining what we might learn by looking at this collection of young eclipsing binaries as an ensemble. And so one of the standard tests is to ask, to what extent do different stellar evolution models, isochrones, to what extent do they correctly predict the mass of a star in an eclipsing binary if you put that star on an HR diagram and you compare it to one of these stellar models? What does the stellar model say the mass should be, and what do you know the mass actually is from your eclipsing binary analysis? So here's 6 different generations of stellar models for pre-main sequence stars, and what you're seeing on the x-axis is the actual mass that we measure dynamically from the eclipsing binary, and the y-axis is the fractional difference between that known mass and the mass that this stellar model would predict from the star's position in the HR diagram. And you see that there are some models, like the Dartmouth models, that do relatively better, but we're still talking about scatters of up to 50%. There are earlier generation models that the scatter is like 100%. So this is a problem that we've had for a long time in star formation research, is that these pre-main sequence stellar evolutionary models really have problems mapping HR diagram quantities into fundamental properties like masses. So I don't expect you to decipher this diagram. This is just to tell you that we looked painstakingly at every single system, right, Willie? And we tried to, we considered every single measurable property of the star, and we tried to ask what were the patterns, and basically we had a hard time coming up with any overarching, meaningful conclusion for why some systems just behave really poorly compared to the models, and other models behave really very nicely compared to the models, until we asked one more question, and that is, what if there's a third star? And it turns out that the young eclipsing binaries that do not have a third star, at least not a known one, and these eclipsing binaries are extremely well studied, and so we have pretty good confidence that if there were a third star there, we would know it. The ones that don't have a third star are the ones that behave really pretty well compared to standard models. The ones that have tertiaries are the ones that, in general, are much more corrupted. And so that got us thinking about what might the effects of a third body be on the measurable properties of the two stars in an inner eclipsing binary. So that brings me to another one of these unusual eclipsing binaries. And this is one that always reminds me of this great photograph from Diane Arbus, because you have these two identical twins and there's something eerily different about them. So this is an eclipsing binary system, again in this very young cluster, where the masses of the two stars in the eclipsing binary are identical to about 1%. Here's the mass ratio. But the temperatures differ by about 10%. The radii differ a little bit. And so here you have two stars of identical mass and presumably identical age, assuming they were born together, but where the luminosity is 60% different. Okay? So identical twins by mass, but very, very different properties otherwise. And so we did some investigations, and I don't know what to make of it. I'm not going to describe this diagram to you in detail. I just really want to point out that, so what we did was we asked, well, what if this third body, I'm sorry, I should have said explicitly, this is one of those eclipsing binaries that has a known third body. And so we asked the question, what if the third body, given some reasonable estimates for the orbit of the third body and so on, what if that third body is somehow perturbing the inner body, the inner binary pair, causing some injection of tidal heat, I don't know what. So we did this in a bit of a hand-wavy way. But we did do some tidal evolution calculations, and I'm not going to describe what all these different curves mean, but I just want to point out that the amount of power that it would take to cause this kind of a difference in luminosity is about 10 to the 26, 10 to the 27 watts. What's so special about that number? That number is order of magnitude the orbital power of the third body in the system. So we thought, at least energetically, there seems to be some, maybe it's just a coincidence, but there could very well be some direct influence of the third body on the properties of the inner binary. So this then connected to some other work that a couple of my students were doing, where we were trying to identify very wide binary star systems in the Sloan Digital Sky Survey, and to then study hierarchical, higher order multiple systems. And the upshot of that work, and I'm sorry to Sarav and Trey because I'm doing one slide for what was a full dissertation, but the upshot of that work is that when we find these very, very wide binary systems in the field, very often it turns out that in fact it's not a binary but a hierarchical triple system. And the wider the apparent binary pair is, the more likely it is that one of those apparently single stars in the wide binary is actually itself a tight binary, right? And that is similar or complementary to work that Andrei Tokovinin and others have done from the other direction, which is to ask what fraction of tight binaries actually have a distant tertiary companion. And it turns out that the tightest binaries overwhelmingly have a hierarchical triple structure. So all of this work from different directions really seems to be pointing to a very clear dynamical evolution of tight binaries that become tighter over time through a dynamical interaction with their third bodies, and vice versa, their third bodies becoming dynamically distanced as the tight binary becomes tighter. So we know, I think, from this kind of work that these three-body dynamical interactions are occurring, and so I think it stands to reason that that dynamical action can be impacting the properties of the binary stars in the ways that I showed you. One last thing to mention along these lines is that I have a couple of students now who are asking the question, if we carefully map the fraction of binary stars in young clusters of various ages, can we actually detect this dynamical, hardening of the close binaries and widening of the tertiaries over the span, over the early evolutionary span of young clusters? And we've just submitted this work, so we'll see if it stands up to the referee. But we have an early indication that, in fact, maybe we can see this happening, where the binary fraction in a really young cluster like NGC 1333, these are posterior probabilities. In a really young cluster like NGC 1333 is about 10% or less. But then, as you go to slightly older clusters, up to about 10 million years, the tight binary fraction increases. Okay, so we think we're seeing the tightening over the span of the first 10 million years, so that the apparent binary fraction goes up. But then, as you start going to field star ages, now the binary fraction goes down, presumably because these binaries become disrupted over time.
You mean spectroscopic binaries by tight binaries?
Yes, that's right. So this is, as I say, this is work that's just being submitted, but I wanted to share it with you because this is work from some of my current students. But I think it's also tantalizing that we can begin to actually map out these dynamical processes that play out in binaries and triples by studying clusters of various ages. Okay. I'm going to do a little transition, all right? So that was the road richly traveled, inspired by a couple of really interesting eclipsing binary systems. But I also mentioned Gaia in the title of the talk, and Gaia is going to really revolutionize all sorts of areas of stellar astrophysics and exoplanet science, as I'll show you. But again, it's eclipsing binary stars, as I hope I'm about to convince you, that are going to be essential to really making full harvest of what Gaia can do. So this guy, and Willie, it's hard to find pictures of you on the internet. I don't know if you knew that, but I found this one. So Willie and I had this idea a while back where we thought, these eclipsing binary, these are benchmarks. And in principle, they're fantastically accurate benchmarks. And we tend to think of trigonometric parallaxes as sort of the most fundamental thing. And of course, they're tremendously fundamental and important. But I probably don't have to tell you all that there have been cases where trigonometric parallaxes have fantastically failed. And so we thought, as we get ready to have Gaia revolutionize everything, what if we can use these benchmark eclipsing binaries as a way to really make sure that these new trigonometric parallaxes are on solid footing? So we put together a set of 150 eclipsing binaries that we expected were going to be in the Gaia first data release. And so because as I mentioned at the beginning, because we know the radii and the temperatures of the stars directly from the analysis, we know their bolometric luminosities. We don't have to invoke distance here at all. We know the bolometric luminosities. We now have, between GALEX and APAS and 2MASS and WISE, we now have the ability to assemble full spectral energy distributions from the ultraviolet to the mid-infrared for many of these stars. And so that gives us a way to directly and quite accurately, as I'll show you, measure the bolometric fluxes of these systems. And so now, as it turns out, these bolometric luminosities for these eclipsing binaries tend to have precisions of about 10% or a little bit better. The bolometric fluxes have really, really fantastically good precisions, but you win because of the square root. And so we can measure the distances to these eclipsing binaries with an accuracy of about 5% or better. So we thought, okay, well, here's the famous case where trigonometric parallaxes failed, right? Hipparchus got the distance to the Pleiades wrong. It took a while for everybody to agree on that, but these other ways of measuring the distance to the Pleiades were all in agreement. And so recently, Trevor David and Lynn Hillenbrand and I and others took this idea of a benchmark eclipsing binary to independently test distances. And we used this new eclipsing binary in the Pleiades, and we used this method that I just described to infer a distance to that eclipsing binary in the Pleiades, and sure enough, it agrees with everybody else about the distance to the Pleiades. So we thought, okay, how about we apply this en masse to all of these eclipsing binaries that Gaia is going to observe. So here's the basic methodology. For each eclipsing binary, we have two stars whose radii and temperatures we know, and therefore whose luminosities we know. We also have these broadband photometric measurements of combined light for the two stars in the eclipsing binary. And so in principle, we just have to add together two atmosphere models, cruise atmospheres, next-gen models, whatever you like. You just have to add them together, and then the only free parameter is extinction. So, here's an example of a system that has very little extinction, so we just add together the two stellar atmospheres and we get a beautiful fit to the data. Here's a case where you add together the two atmospheres and you get a spectral energy distribution that looks like that, but now you just introduce reddening as the one free parameter, and now again you fit the data beautifully. Okay, so this is the basic idea. And now we can just add up the flux from this fit to the photometric measurements, and we have our bolometric flux at Earth. And so we showed in this picture, Willie and I showed that the typical uncertainty in those bolometric fluxes is a couple of %. So that doesn't dominate the error budget. And the distances, or rather the parallaxes that we infer for this eclipsing binary sample we showed, has a typical precision of about 200 micro-arcseconds. 200 micro-arcseconds for these eclipsing binaries. And just be very clear, this is a totally independent way of measuring the distances. We haven't used a parallax here at all. So this is a set of predicted parallaxes. And what really amazes me still, I don't know if this amazed you, Willie, but it totally amazed me at the time, is, so the first thing we did was we asked, well, did Hipparchus get the answer right for these 150 eclipsing binaries? And this is showing you that within the expected distribution of the errors, basically there's no evidence that Hipparchus got the answer grossly wrong for any of these eclipsing binaries. What really amazed me is that the color coding here is showing you what fraction of the bolometric flux that we measure is actually coming from beyond the span of the photometric measurements, right? So, you have a case like this. You have a case like this where 99% of the bolometric flux is contained within the measurements. Then you have a case like this where maybe only 5% of the flux is contained within the photometric measurement. So you might think, oh my God, you're extrapolating 95% of the flux. What are you doing? Well, the fact is that there's only one free parameter, so it's not really an extrapolation in that sense. And so what we found, this is very encouraging, is that even in those cases where we're quote-unquote extrapolating 90% or more of the bolometric flux, Everything just works out great. So we thought, all right. And because we're not using parallaxes here, right? We're just using we're using the Stefan-Boltzmann law, then limited only by the precision of the photometry and the bolometric fluxes, this method doesn't care about how far away the system is. Okay, so then Willie and I said, all right, so now let's see if Gaia got the answer right when the Gaia DR1 parallaxes came out. And here's the quick answer, is that there's clearly an offset in the Gaia parallaxes relative to this benchmark eclipsing binary sample to the tune of about 260 micro-arcseconds, in the sense that the Gaia parallaxes are systematically too small. Okay, so in the Gaia first data release, the distances are systematically a little bit too far. There's some evidence that maybe it depends on the ecliptic latitude, and that actually makes sense given the way that the Gaia measurements are made. That's not entirely clear. For now, the upshot is that we really can use these eclipsing binaries as a fundamental independent test of trigonometric parallaxes, and there are indications of small problems in the DR1 Gaia data, but they're not all that bad. Speaking of Gaia, coming back to the radius inflation question, Garrett and an undergraduate working with me at Vanderbilt, we thought, all right, now that we have Gaia data for some of these stars, let's go back and ask that Pleiades radius inflation question, but now with direct distance measurements to some of these stars. And so what Garrett showed in this paper that we just had published is that, and now these are direct. Let me be careful. I was going to say these are direct measurements of radii. I realize that might imply that these are interferometric measurements or something. What I mean to say is that these are radii that come not from some stellar model or something. These are radii that come from the Stefan-Boltzmann law. Right? Now we have distances, so we know the bolometric luminosities, and so we can back out the radii via the temperatures and the bolometric luminosities. And so what Garrett showed is that there really are Pleiades stars whose radii are considerably larger than they should be for a coeval population. And what he further showed is that it's directly related to the spins of the stars. So you have relatively slowly rotating Pleiades stars whose radii are basically what they're expected to be. And on average, the inflated Pleiades stars are the ones that are spinning fast. So this now kind of triangulates on the story that I was telling you earlier about the relationship between stellar spin, magnetic activity generation, presumably the impact on internal convection, and the puffing up of the stars. So this is just a nice example, I think, of how these Gaia parallaxes are going to really help us address some of these fundamental stellar astrophysics questions. We also started thinking about how Gaia, by virtue of allowing us to make precision measurements of stellar properties in the ways that I've been showing you, will therefore, in turn, allow us to derive much more precise properties of planets that orbit stars. And so I'll tell you that this was a great bit of fun for me and my team. We made it our goal, for no good reason other than just for the fun of it, to see if we could publish a paper, post it on arXiv anyway, that would make totally empirical measurements of stellar radii and masses for as many of the known planet-hosting stars as we could, and therefore direct radii and masses for transiting planets around those stars. And our goal was to do that within 24 hours of the Gaia first data release. And I don't know if you know this, but I'll tell you, the Gaia first data release was early in the morning on September 14th. And here's the paper posted on arXiv on September 14th. Again, no good reason for it other than just for the fun of it. But so what we did here was we used the Gaia data, the Gaia first data release parallaxes, together with the methodology that I just described to you for eclipsing binaries, in order to empirically measure the radii of 116 transiting planet host stars, and then basically through a series of steps that I'll show you, we're able to get the masses and other properties. So here's the basic idea. I've shown you this already. We can directly measure the bolometric flux for a star, all right? We also, if that star has a transiting planet, this is, I think, familiar to many of you, you can, in essence, get a measure of the stellar density from the properties of the transit and the orbit. And so with the bolometric radius, and now we just need to also know the temperature, but many of these stars have well-determined temperatures. We get an angular radius. Now we have a Gaia parallax, so we can turn that angular radius into a linear radius. With the radius and the density from the transit, we get a mass, right? And then the planetary radius and mass is directly related to the stellar radius and mass, okay? All empirically determined quantities, and it's the parallax that really kind of brings it all together. So this was really and truly sort of the primary motivation for doing this work, was to really just sort of lay out a methodology that would bring all of these pieces together. And so I was going to convince you why this was important, but I hope I don't have to convince you of that. So this is what we were able to do. The typical precision that we can achieve in the stellar angular radii is about 3%. And in absolute units, the uncertainty on the stellar radius is a couple of micro-arcseconds. And so this then is what the stellar radius uncertainty looks like as a function of the parallax or distance for the sample. The blue highlighted stars are the ones that have transiting planets. The non-blue highlighted stars are the ones that have Doppler planets, non-transiting planets. And so what you see is that the relationship between the uncertainty on the stellar radius and the stellar distance actually follows very nicely what you would naively expect given the nominal uncertainty in the Gaia parallaxes. And so this is then what we expect is going to happen to this distribution of stellar radius uncertainties when we get Gaia DR2. Okay, so all of these things are going to move down like this. So we're going to have stellar radius uncertainties of a percent or less in many cases. And then this is what the masses look like. So currently the typical stellar mass has an error of about 10 or 20%, but this is what's going to happen with Gaia DR2. Okay? And this is just measuring bolometric flux and a parallax and the duration and depth of a planetary transit. And so I love this. I don't know, I geek out on stellar astrophysics, but, you know, I started this out with Henry Norris Russell and everything, so it seemed appropriate. This is an HR diagram of all of those planet-hosting stars that we analyzed in this paper, where everything shown here is determined totally empirically. So the bolometric luminosities, the temperatures come from a spectrum. The symbol size here is proportional to the radius that we measured directly, as I showed you. And so this is kind of fun. You can actually see, so here the red points are metal-poor stars, the blue points are metal-rich ones. And so you can actually see, and this is supposed to happen, you can see the separation based on metallicity of stars on the main sequence. But we can also do other things. So again, these are all totally empirically measured properties. So now let's look at the planets. Here is what the planet radii look like as a function of planet mass, color-coded by the amount of insolation that the planet receives from its host star. And so you see there's this sort of nice relationship between planet radius and planet mass. But then when you get to these hot Jupiters, there's clearly a separation where the more highly insulated planets have larger radii for their masses. So this is, this was known before, but now we have this in a in a completely empirical way. Okay, so as I said, currently we get these properties here now for the planets. Our typical uncertainty on the planet radius is 9%. Typical uncertainty on the planet mass is 22%. But once we get to the second data release from Gaia, this is what we expect to be able to do using this methodology. Okay. Now, interestingly, there were some stars and some planets whose properties are changed from what we thought they were now that we have accurate distances. In general, for the transiting planet host stars, you see this is how much the stellar radius changed as a function of how much the distance changed based on what Gaia measured compared to what was previously presumed. And so not a whole lot of change there, so some outlying systems. But it's really in the Doppler stars where in some cases we have Gaia has revised the stellar distance by up to 100%. And so as a result, the stellar radius is changed by that amount and the planetary properties change as well. There's another interesting question that we can address with these planet-hosting stars, and this is that there has been some debate in the literature involving some of your colleagues about the true nature of what have been referred to in some cases as retired A stars. And so that's talking about these evolved planet-hosting stars, right? So you know that it becomes difficult to estimate the masses of stars as you get to the subgiant and red giant branch because the stellar evolutionary tracks kind of converge. And so some folks have said, these evolved stars are the, used to be relatively hot and massive main sequence stars. And so any planets or lack thereof around them is telling us something about what happens to planets around massive stars. Other people have said, no, they're actually lower mass stars. It's hard to measure their masses. Now we have a population of planet-hosting stars whose masses we've measured empirically in the way that I just showed you. And it turns out, so you see that the vast majority of these subgiants and giants are colored blue and green and purple. So it turns out overwhelmingly these are massive stars. They really are retired A stars. So I'm sorry that John isn't here to gloat, but this one's for you, John. I point out this thing about retired A stars because the KELT exoplanet transit survey and some of the other ground-based transiting surveys have been finding planets around relatively hot main sequence stars. And this, as it turned out, is going to be something that's going to be true for TESS as well, especially in the full-frame image data set, just by nature of the Malmquist bias that brings us more hot stars into our bright star sample. And so I just wanted to highlight one brand new exciting planet from the KELT survey. We've just submitted this work. This is an HR diagram of planet-hosting stars that are known. And this brand new one, KELT 9, is the first bright A star with a transiting hot Jupiter. And its planet has the temperature of an M star. And very large scale height. And so it's going to be a really interesting system for studying properties of hot Jupiters around hot stars. But more importantly, as I said, since TESS compared to Kepler, TESS, the full-frame image data set, is going to be bringing us lots of these A stars, maybe even B stars in some cases. We're now going to be in a position where we can directly map what happens to planetary systems, the demographics of planetary systems, from their massive star progenitors all the way into their evolved older stellar counterparts. Let me skip over this so that I can wrap up, because I want to say that there's one more thing that we're going to be able to do in the era of TESS and that is that, as we've demonstrated with Kepler, we'll be able to use the precision light curves from TESS to directly measure the granulation on these stars, and from that granulation, directly measure the surface gravities of stars with very, very high precision. So this is work from my student Fabian Bastian that some of you may be familiar with. The point here is just to say that in the era of TESS and Gaia, we'll have direct empirical measurements in the way that I just showed you of these various fundamental stellar properties, and then add to that the ability to extract from the light curve data accurate measures of stellar gravity and evolutionary states. David Kipping showed that this stellar granulation flicker, as we called it, can be extended to accurately measure the densities of the stars from the granulation amplitudes. And so we project that with TESS we'll be able to do this for about 100,000 of the TESS postage stamp stars. So this is an incredible confluence of the ability to measure basic empirical properties of stars and the planets. And so, this will usher in, forgive me, this era of stellar astrophysics and precision exoplanetology. So let me end by trying to bring this all full circle. Henry Norris Russell begat Shapley, begat Ivan King, begat Bob Matthew, begat the person standing in front of you, begat Fabian Bastian. And what I think is so lovely about this arc of history is that, the HR diagram that bears Russell's name is still so integral and fundamental to how we think about stars and stellar astrophysics, stellar evolution, and planets and everything about them. And over 100 years later, what Fabian would create is an entirely new way of representing essentially the HR diagram, but now involving properties that emerge from the data products that we get from things that we will get from things like TESS and Gaia and so on. And so I promised in my abstract something that maybe would surprise you, and that's a connection to autism. So here it goes. This discovery that Fabian made in the Kepler data of the stellar granulation and surface gravities and so on, she made using a data visualization tool that some of you maybe are using now. It's available for free. That was created by an autistic computer science student that I've employed in my group. And the way that this came about actually has some personal origins. This individual going to this esteemed institution has autism, and this has gotten me thinking a lot about autism, its challenges, but also its strengths and unique capabilities. It turns out that there's a literature emerging around, in many cases, the unique capabilities of some autistic individuals, specifically when it comes to things like data visualization, pattern recognition, ability to recognize patterns in new and unusual ways. There's a documentary that I recommend from the Simons Foundation called The Colors of Math that talks to mathematicians and Fields medalists about how they don't think about math symbolically, they feel the math, they think in terms of colors. It's really fascinating to think about this sort of idea of visual cognition and how it can lead to new kinds of discovery in a field like ours. And I was trolling the internet, as we do, and I came across this fantastic quote from Feynman. He says, what I'm really trying to do is to bring birth to clarity, which is really a half-assedly thought-out pictorial semi-vision thing. I would see the jiggle, 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 or the wiggle of the path. Even now when I talk about the influence functional, I see the coupling and I take this turn, like as if there was a big bag of stuff, and try to collect it away and to push it. It's all visual. It's hard to explain. And so I'll leave you with this. I started working with a computer science colleague and a neuroscience colleague at Vanderbilt as part of an initiative to try to understand what it is that autistic individuals see when they look at data patterns. And we can actually map, we can track eye movement, we can measure how much time is spent on various visual displays. And it turns out that Tukey, decades ago, the Princeton statistician, sort of very presciently thought about this and said, if you think about data in a purely visual way, what is it that really makes a data visualization interesting, and perhaps in a way that leads to discovery? And he sort of suggested this thing that he called scagnostics, interesting features and data displays. And it turns out that Fabien's discovery, using the filter graph tool that was created by my autistic computer science student, has a very, very high scagnostic score along various of these visual properties. So, I'll end there. I hope that wasn't too much of a scattershot approach to you, but I'll let Henry Norris Russell have the final word, and I'll thank you for your attention and happy to take your questions.
Okay, great. Questions for Kayla? Let's see, Charles.
So you did this very interesting thing with the first Gaia data release, and you got an offset between your different binary distances, and I think you attributed the error to Gaia. Did you not?
You would think correctly, yes.
So why should we believe you?
Well, because Willie Torres is a smart guy, and as I would say a couple of things. First, we tried to show with the Hierarchical parallaxes that this methodology of measuring the distances to these eclipsing binaries, really works and is robust. We see no offset like this in the Hierarchical parallaxes for those 150 eclipsing binaries. Take those same 150 eclipsing binaries and test them against the Gaia parallaxes. Now we see 260 micro-arcsecond offset. So that's the first answer. The second answer is that it turns out that a couple of other groups have looked at the same question, but using other benchmark objects. I think none quite as benchmark as our eclipsing binaries. But Adam Reese and a postdoc put out a paper where they looked at some Cepheids, and they found in the most nearby Cepheid, most of the Cepheids are really far away, but in the most nearby Cepheids, they saw a hint of an offset in the same direction, in the same magnitude as what we saw. There's another group from Georgia State that looked at a set of nearby M dwarfs with long-term, well-measured parallaxes. They see the same offset. Anyway, we got it right first. But
Is there a discussion going on? Has the Gaia team responded and said?
No, we haven't asked the Gaia team to respond. I haven't heard of a response. They did the community a favor by putting out this first data release. Mm-hmm. Originally, the plan was that there weren't going to be parallaxes at all until the second data release. So, I just want to be clear. These first data release parallaxes, by and large, are fantastically good. And really, I just wanted to show that eclipsing binaries are so fantastically good that they can be used to actually test trigonometric parallaxes.
Yeah.
Going back to the very beginning of your talk, you're eclipsing brown dwarf here. You show really convincingly how much you can learn once you establish this eclipsing binary properties. But it also occurred to me that this assumption or this finding that there's no circumstellar material around is key. And a lot of the properties, it seemed to me, could be explained if you had a disk that was close to that more massive component. It would look inflated, it would look like a lower temperature. So how confident are you that you ruled out a possibility of an inner disk or a close-in disk?
Yeah, how confident am I?
What's the separation of the components?
Oh gosh. Well, so the orbital period is 9 days.
9 days, okay.
It's like...
So they're very close.
It's like 0.05 AU.
So it may not be that plausible, but still it's worth thought.
So, so there's no evidence at all of an excess all the way out to 20 microns. be hard to hide a disk.
No, but the disk that you would be worried about would be mostly emitting at 2 microns or shorter wavelengths. And, you know,
But not at all at 20 microns?
I don't know.
Anyway, I think the evidence is pretty good that there's nothing there.
And second question,
Yeah.
when you talked about the Pleiades, and you had an interesting HR diagram, it showed that the stars that were more quickly rotating were slightly above.
Yeah.
And then you had an interpretation dealing with the magnetic fields. So say if that's correct, then can't you also constrain the coevality of the Pleiades? Can you say something about that?
So I think what you're saying is that if we think we at least have an empirical understanding of this effect, then we can basically correct out what would otherwise appear to be a not. Yeah, we can sort of collapse this apparent non-coevalent. That's a good point. We haven't tried that.
Because you would expect
should do that.
if there was an age spread,
Yeah.
that the younger stars would be rotating faster.
Yeah. Sure.
So that would, I mean, you could interpret that as some kind of an age spread too, maybe, I don't know.
Yeah. Well, that's a good idea. Thanks, John.
So this is kind of similar in the sense that, in stellar evolution, we have the idea that you have a binary system that are similar in equal mass, and we assume that they're contracting down the pre-main sequence. They should have the very similar properties, but you're showing that, like in the brown dwarfs, you have two stars that are very different activity levels. They're rotating very differently. So how do you get that?
I don't know.
Is age just a relative thing? Are these two stars that should be coeval but aren't?
So are you talking about a particular system?
Well, in the brown dwarf system, but then also in the PAR 1802 and things like that, where the two stars appear to have different ages, but that
Yeah. So in the dissimilar identical twins case, there the orbital period, I didn't tell you the orbital period, but I'll tell you now, it was about 4.5 days. So those two stars in that eclipsing binary are actually tidally synchronized. So they have the same rotation rate, but because they're tidally synchronized. In the case of the brown dwarf eclipsing binary, they are just wide enough at 9 or 10 day orbital period that we actually wouldn't necessarily expect them to be tidally synchronized. So I would say it never particularly surprised me that the two brown dwarfs didn't have the same rotation rate. You're asking sort of
if rotation is
first
dictated by
principles,
attractions,
why don't they have the same rotation?
Right.
I don't know.
To make another connection, in the case of emerging black holes, some people have suggested models where you might have two stars that start relatively close to each other and they're spinning rapidly, and this affects convection. And so you have more mixing within these stars. But it seems to me that your work also may have something to say about that. I'm not sure if you look at the mass ranges,
Right.
different in different mass ranges.
Yeah.
I haven't
I haven't considered
considered that.
that, but just to sort of explicate what I think is in your question, just to make sure I'm hearing it right, and for everybody else. It's sort of counterintuitive the way that the effect goes, right? Because you would think you spin the star faster, it should make the inside move around more, and so that should deplete the lithium faster, all that kind of stuff. And in fact, what seems to happen is you spin the star faster, and you as a result, you crank up the magnetic field, and that in turn actually suppresses the internal convection. So that is the nature of the effect. I think that's a pretty clear inference from this work. As to whether it maps onto what you're talking about, I don't know.
And then, if you don't mind, may I ask a question?
Yeah.
So, you've got the masses for stars empirically for the transiting systems.
Yeah.
One of the intermediate steps was you're basically converting the transit duration into the stellar density.
Yeah.
Okay. So you have to know the velocity at which the apparent velocity of the object across the star. So do you worry about eccentricity?
Right.
And then, so how did you handle that? But then looking forward, if in the future, we have two ways to estimate the masses of all the stars in the Kepler field.
Yeah.
I'm sure you guys have thought about all this. You know what I'm about to ask. So you have now these two independent ways to estimate the masses of all stars in the Kepler field. can you then deduce the underlying eccentricity distribution of all the planets without having to get radial velocities?
Yeah, that's a great question. So I think the answer is yes. The first part of your question was how did we handle that? And the truth is that we swept that under the rug a little bit. We basically said, look, these are short period systems. We're really pretty sure they're circular orbits. In any case, we're going to treat them as circular orbits.
Okay, so treat it as circular.
Treat it as circular. But indeed, thinking ahead, so this is something that that Dave Kipping showed in this paper that I made reference to, where the primary result here is that the granulation flicker can be used to measure the stellar density as well as gravity. And then he goes on, I didn't mention this, but he goes on to show that if you have this independent measure of the stellar density, now you can do this, what he calls astrodensity profiling, and back out the eccentricity. So I think absolutely.
So for the Kepler field, we'll get that with maybe DR2.
Yeah.
Great. Okay, wonderful. Well, you've been working hard the last 2 days. We're going to take you out for dinner.
Yay!
And then you get to go home. But first, we're going to thank you again for this talk.